motion. Quick review. Displacement. The vector, so it's going to locate the object for you on a coordinate system. Angular displacement is going to be the angle. Proper unit is radians. Average speed is measured distance over measured time, or how fast the location changes in time. Average rotational speed is how fast the angular displacement changes in time. Proper unit is radians per second. Average acceleration is how fast the measured velocity changes in time. And the average rotational acceleration is how fast the angular velocity changes in time. Arc length is the length of this curvature. You can figure out the length of this curvature if you know the angular displacement and the distance, radial distance to that curvature. So multiply the angle with the radial distance. Tangential speed is the speed along the direction of the curve. You can figure that out if you know rotational velocity multiplied by the radial distance to the curve. That's it. All right, speedometer is going to measure the rotational speed of the car. If you got larger wheels, rotational speed, speedometer is going to give you the same speed, except the car is going to be moving faster than what's indicated on the speedometer. Because when you take the rotational speed and multiply it by the radius of the tires, it's going to give you the tangential speed of the tire. So which means that the car is going to move faster than what's on the speedometer. Tangential acceleration is the acceleration along the direction of the curvature that you curve. You can figure out the tangential acceleration. If you know rotational acceleration, you multiply it with radial distance to the curvature. There's a centripetal as well as the rotational acceleration. You do have actual addition of the accelerations. Find the hypotenuse of it. What else? Motion becomes predictable when the acceleration is constant. Rotational motion becomes predictable when the rotational acceleration becomes constant. Inertia is a measure of, it's the same as tendency of an object to retain its initial motion. Or resistance to change of motion. Motion means velocity. All right, so what causes inertia is mass. Moment of inertia is a rotational mass. Rotational inertia. What else? Potential energy is stored energy. Energy could be stored doing work against gravity or restoring force. Kinetic energy is the energy of motion related to the square of the speed. Mechanical energy is a combination of kinetic and potential energies. Conservation of mechanical energy means the mechanical energy is constant. Okay, the only thing I'm interested in from this section in terms of review is this term. All right, so this term is the moment of inertia, otherwise known as the rotational inertia. Rotational mass is okay, so there's a rotational mass like term, let's say. I don't want to say rotational mass, I want to say rotational inertia is probably better. So moment of inertia is a rotational inertia. It depends on the mass, it also depends on the square of the distance to the point of rotation. All right, so remember you go from linear expressions to rotational expressions. All right, so force becomes the rotational force. Acceleration becomes the rotational acceleration. Mass becomes the rotational inertia or rotational mass. Okay, so that's it. Rotational kinetic energy can be obtained from tangential kinetic energy. All right, guys, you got the regular kinetic energy, so this is your tangential velocity. Okay, so we got something which is rotating, that's what it means. This kind of a tangential velocity. Tangential velocity is going to be caused by a rotational motion, so it could be expressed in terms of the rotational velocity. mr squared is going to be our rotational inertia. So we do a back substitution and we end up getting the rotational kinetic energy. All right, so tangential kinetic energy can be expressed in terms of rotational kinetic energy. M becomes I, so mass becomes the rotational inertia. And linear speed becomes the rotational speed. Okay, so it's got a subscript, R means rotational. And this time, this should have a subscript that's going to say T, so it's tangential. Tangential implies rotational motion. So we got rotational kinetic energy. And we also have a tangential kinetic energy. Tangential implies rotational motion. So tangential kinetic energy can be expressed in terms of the rotational kinetic energy. All right, remember the rotor, you become suspended on the wall. All right, so imagine that we got a rotor and it's being accelerated from 0 to this revolutions per minute, a little bit over 8,000 revolutions per minute. All right, so and then this rotor has that moment of inertia, which is this. So the question is, how much energy is required to actually bring from rest to that speed? Okay, so how would you even list something like that? Okay, so which means that we have to transfer energy to it. So we have to feed energy into the system. Energy that you feed into the system is given to the system through work. Work is a process of transferring energy. And the energy that you transfer is going to be transferred in the form of kinetic energy. All right, so that's what it means. So which means that it's going to go from initial rotational speed to a final rotational speed. The question is how much energy needs to be transferred to it. So what's the amount of work that you have to do? In essence, the amount of work that you do is going to go into the rotational kinetic energy of the system. All right, so this capital W is the work that you need to do. So in essence, what's happening is you're changing the angular velocity. So the initial angular velocity is going to be 0. All right, okay, that's it. Setup is the most important part. This is more of a demonstration problem. Plug the numbers in. We'll get our expression in terms of joules. It makes sense to convert things to units that we understand. So it's going to be calories. So it's going to take 3 calories of work to get it up to speed. Right, from a physics perspective, this is a concept which is important. This is an eye-opener. Then kinetic energy can be expressed in terms of 2 types of kinetic energies. I'm going to introduce a new kinetic energy that we've been using for a while without noticing. This is not the tangential kinetic energy. This is the translational kinetic energy. Because we keep using the same subscripts for everything. So I'm just going to tell you what this is. This is the translational kinetic energy. And this one is a rotational kinetic energy. We discussed this one before. All right, so the thing we're discussing is the translational kinetic energy. So what's the meaning of the translational kinetic energy? Translational kinetic energy is going to be referred to the kinetic energy of rolling objects. All right, translational kinetic energy is the kinetic energy of the center of mass. This thing has a center of mass at the center of geometry. So the only thing we do is we follow the translational motion of this ball. Translational motion is the linear motion. So it's the displacement of this ball. All right, so instead of saying this is the displacement kinetic energy or linear kinetic energy, we call it the translational kinetic energy because in essence, this ball is getting translated in this direction. Okay, it's just a technical term. So translational kinetic energy refers to the kinetic energy of the center of mass. We were always interested in the motion of center of mass. Every time I would draw a ball or a dot in the physics box, you're always interested in the motion of the center of mass because that's the simplistic motion. And the kinetic energy of the center of mass has always been 1/2 mv squared. But the real life is you got this translational kinetic energy, which is the kinetic energy of the center of mass moving in this direction. As the center of mass is moving, notice that the rest of the ball is rotating with respect to the center of mass. So which means that it's also got a rotational kinetic energy. All right, so it's got the translational kinetic energy of the center of mass, and it's also got the rotational kinetic energy with respect to the center of mass. So we've got 2 types of kinetic energies involved in this one. So what you need to do is just sum up. You got the translational kinetic energy of the center of mass. It's also got the rotational kinetic energy with respect to the relative to the center of mass. So it's got 2 kinetic energies. So total kinetic energy is going to be both the translational kinetic energy as well as the rotational kinetic energy. Here's the application of it. It's kind of weird because we weren't getting a full picture of physics because we always kept looking at the kinetic energy of the center of mass, ignoring what was going on relative to the center of mass. Okay, so take a bowling ball, for example. And let's take a look at the total kinetic energy of the bowling ball. Okay, we got a bunch of numbers for those of you guys who enjoy numbers. Okay, this doesn't really require numbers. I'm just interested in the total kinetic energy. Small bit of a derivation that you need to know. So this is the translation kinetic energy of the center of mass. Theta this time, I'm using theta. There are 2 ways of expressing rotational kinetic energy. You can use R or you can use theta. In this case, I'm using theta, so that refers to the rotational kinetic energy, which is the same as this. Translational kinetic energy is going to be 1/2 mv squared. Rotational kinetic energy is that. All right, now sum them up. All right, and then I want to come up with a one unified expression that's going to have final speed in terms of the linear speed. And from maybe have to get to that, number one, this moment of inertia, rotational inertia needs to be expressed in terms of mass. So we have a bowling ball. So let's get an expression for the bowling ball. All right, so you got the uniform sphere. So that's the bowling ball that you're looking at. All right, so it's going to be 2/5 mr squared. And then what we have to do is just do a back substitution. All right, so it's something weird happens. All right, I gotta share it. Okay, so I simplify the terms on the right hand side. This R omega can be expressed in terms of the tangential velocity. And all of a sudden, I'll do that. And then this is a sobering moment. I don't care how tired I am. All of a sudden, I know what needs to be on the left-hand side. I expected to see, this is the tangential velocity. Here, I was expecting to see the translational velocity. All right. So I go, okay, so go back to change those terms to the translational velocity. Okay, they look the same, but are they the same? Okay, so being a physicist, it's a bit of a curse at this point. Now, if you're not a physicist, you're thinking they're the same things, but if you're a physicist, you have to kind of check to see if they are the same things. If they are the same things. Okay, so guys, translational kinetic energy is the kinetic energy of the center of mass. And tangential kinetic energy is the kinetic energy right at the edge. Okay, so translational kinetic energy is going to give you the speed in this direction, and tangential kinetic energy is going to give you the speed in that direction. Guess what? They will be the same. Tangential staying. So which means that now we got common terms. Mass is going to be common. The speed is going to be common. Factor them out. And the kinetic energy of the system is not going to be 1/2 mv squared. It's going to be 7/10 mv squared. So it's going to be larger than 1/2. Right, so the kinetic energy is going to be more than what we were expecting. Numerically, I don't know what to do with the numbers because the story ends right here. The physics, as far as physics is concerned, ends there. If it's not multiple choice, you come up with this and express it in terms of calories if you want to. It doesn't mean anything to me. All right. The entire derivation that you're looking at is where the physics is, the interesting physics, something that we can use in the future, which we won't. All right, 7:26. Okay, take a break. All right, so start to make it interesting. So we got this pole. It's like a pole vaulting pole. It's long. I don't know. It's like, what is it, 15 feet or something? All right, so you let it tip over. And then the PowerPoint says, okay, we'll wait. All right, so we'll just let it tip over. So we're interested in speed at the very top of the pole. So this is the tip of the pole. We don't know how fast the tip is going to hit the ground. We got the length. We want the speed in terms of miles per hour. We're assuming that gravity is the only force acting. So the mechanical energy is constant. So final energy is going to be rotational kinetic energy. Potential energy is going to be potential energy. Potential energy of the tip of the pole. So you got the rotational kinetic energy here. All right, so the initial height is going to be here, so it's going to be the same as the length of the pole. So that becomes L. All right, try again. All right, so I'm having a shot for the pole. So now let's go to our table. So the pole is obviously it's a rod that we're looking at. So it depends on the rotational axis. If it's in the middle, we use this formula. If it's at the edge, we use this. So the pole is sitting on a ground, just like so. It makes sense to use this one. So it's going to be 1/3 ml squared. So our moment of inertia is going to be that. So we do a back substitution. Right, so our tangential speed is going to be related to the rotational speed. So let's try to isolate the rotational speed. So get rid of the like terms. I'm just going to let the animation run for a while. So mass disappears. And I'm moving everything from left to right, getting rid of the like terms. Okay, so now we got the rotational speed. Rotational speed could be expressed in terms of the tangential speed. The rotational speed multiplied by the radial distance of the rotation. Radial distance of the rotation is going to be the same as L at that point because it's going to arc. The tip is going to arc towards the ground. All right, so we'll do a back substitution. And then now we have to go after V. All right, so we'll do the cancellations and blah, blah. Just move everything from left to right. Get rid of this square, and we're done. So we came up with an expression. So evidently, the speed of the tip, the final speed of the tip is going to be related to the length. No surprise there. Plug the numbers in. Convert meters per second to miles per hour. So we get 26 miles per hour. All right. This was almost interesting. Almost. Not yet. Okay, so let's make things